Hello, this is video number 21 on my single variable calculus 2. In this video, we're going to talk about three different tests for convergence of series. These are all tests that are applied for positive series, which means the series that have positive terms. The first test is integral test. Integral test can be used when you can easily integrate the integrand. So we have to check three conditions. First, we need to check that the function is continuous. Next, the function is positive, and then it is decreasing. If you have the terms of the sequence follow these three properties, and we can easily integrate the function by turning the terms of the sequence into a function, then we can use the integral test. So what's the idea of the integral test and why does this work? So if you look at the integral f of x, and let's assume that our sequence if is f of 1, so this is f of 1, so this is y equals f of x, so this one is f of 1, and then the next one is a2. Well, this one is basically 1, this one is 2, this one is 3, etc. So if you look at these areas, the area of this rectangle here is base, which is 1 times height, and height is f of 1, which is a1. So this area is a1, this area is a2, the next area is a3, etc. So a1 plus a2 plus a3, etc. That is more than the integral from 1 to infinity of f of x dx. Now if you look at the right endpoint integrals, these approximations, right endpoint approximation for the integral, the first area is a2 because it starts from 2 and the height here is a2, f of 2, which is a2. So that's greater than or equal to a2 plus the next rectangle is a3, etc. So if this is finite, then this would also be finite, assuming that everything here is positive. And if this is infinity, then this would also be infinity. So if the right side is infinity, if the smaller one is infinity, then the larger one is also infinity. So in other words, if the integral converges, then the sum converges. If the integral diverges, then the sum diverges. So the integral and the sum behave very much the same. Determine if each of the following converges. So let's try and solve this problem. So the first part is sum of 1 over n. So we have so far learned one test, and that is the divergence test. Test for divergence cannot be used here because 1 over n approaches 0. So 1 over n approaches 0. So test for divergence cannot be used, is inconclusive. So we'll use the integral test. So if you look at the function that gives us the terms of the series is 1 over x. This is clearly a continuous function if we avoid 0. It is also positive because we are starting from n equals 1 to infinity. So over that interval from 1 to infinity, it is positive, and decreasing because the numerator is increasing, x is increasing, so 1 over x is decreasing for x greater than or equal to 1. So we're going to integrate this one from 1 to infinity, 1 over x dx. If this becomes a finite number, the series is going to converge. If this becomes infinity, then the series diverges. Let's integrate this from 1 to t and then take the limit. So this is the limit as t goes to infinity, natural log of x from 1 to t, which is the limit as t goes to infinity, natural log of t minus natural log of 1. And if we let t go to infinity, so that is infinity. So this series diverges. So that's the first one. Now let's look at the second example. The second example is very similar. It is 1 over n squared. So the function is 1 over x squared. So this is also positive, continuous, and decreasing. but we would have to avoid 0. So it would be x greater than or equal to 1 because n starts from 1 to infinity. So this is an decreasing, continuous, and positive function. So we are going to integrate this from 1 to infinity and see what we get. So this is the limit as t goes to infinity. And by the way, we will have to also mention what test we are using. So I'm going to mention that this is true by the integral test. So anytime you're using a test, you'll have to mention the test that you're using and you'll have to check the conditions. So the conditions are continuous, positive, decreasing, and also I check that I mentioned that I'm using the integral test. So let's evaluate this one. This is the integral from 1 to t of 1 over x squared dx. This is the limit as t goes to infinity. Integral of 1 over x squared is x to the power of negative 1 divided by negative 1 from 1 to t, which is the limit as t goes to infinity. Let's plug in t, we get negative 1 over t. Plug in 1, we get plus 1. And as t goes to infinity, this approaches 1. So now because this converges by the integral test, the sum of 1 over n squared also converges. Okay, let's look at the last one. So the last example here is sum of 1 over n natural log of n. So what is the function? The function is 1 over x natural log of x. So this is continuous because there is no 0 at the bottom. It is positive and it is decreasing because x gets larger, natural log is also increasing. So as x gets larger, natural log and x are both increasing. So the denominator is increasing. So 1 over that is decreasing for x greater than or equal to 2. We have to avoid 1 because natural log of 1 is 0. We don't want a 0 at the bottom. Okay, so it satisfies these three conditions. So we're going to integrate this from 2 to infinity of 1 over x natural log of x dx. If this becomes a finite number, the original series converges, otherwise it diverges. This is the limit as t approaches infinity, integral from 2 to t, 1 over x natural log of x dx. This is limit as t goes to infinity, integral, well, how do we integrate this one? We'll have to do a u sub. So u equals natural log of x. 1 over x dx is du. So this is du. 1 over u. When you plug in x equals 2, u is natural log of 2. And when you plug in x equals t, we get natural log of t as the upper limit. Now we will integrate this. So the integral of that is natural log of u, and this one is from natural log of 2 to natural log of t. Let's see what we get. So as t goes to infinity, this is natural log of t minus natural log of 2. Okay, so natural log of 2 is a finite number. As t goes to infinity, natural log of t goes to infinity, which means natural log of that also goes to infinity. So by the integral test, the given series diverges. So again, we'll have to check the conditions. We'll have to mention the tests. So the three conditions for the integral test are positive, continuous, and decreasing. So the first two examples that I did, the sum of 1 over n and the sum of 1 over n squared, are examples of what we call P series. And this is a very useful one to remember. P-test tells us that for a constant P, this series converges precisely when P is greater than 1. So what is the reason for this one? Well, if you look at this 1 over n to the P, 1 over n to the P approaches 0 if P is positive. So if P is less than or equal to 0, then 1 over n to the P is n to the power of negative P, which is greater than or equal to 1 because negative p is positive. So that tells us that 1 over n to the p does not converge to 0. Thus, the series 1 over n to the p diverges by test for divergence. So if p is negative or 0, that clearly diverges. Now let's assume that p is positive. So suppose p is positive. Now if p is positive, we can take a look at this function 1 over x to the p. So this function is decreasing because p is positive, so x to the p is increasing. Therefore, 1 over that is decreasing. It is also positive and it is also continuous for x greater than or equal to 1 because we are looking at the portion from 1 to infinity. Now let's take the integral of this one. So integral from 1 to infinity of 1 over x to the p dx. Well, we can find this one for p not equal to 1, it would be power rule. For p equal to 1, it would be the natural log. So this would be the limit. Let me first write it down as a limit. So this is the limit as t goes to infinity, integral from 1 to t, 1 over x to the p dx, which is equal to, okay, so if p is 1, this would be the limit as t goes to infinity. When p is 1, this is natural log. So this is natural log of t minus natural log of 1. If p isn't 1, then this would be just the power rule. So we can say this is t to the power of negative p plus 1 over negative p plus 1 minus 1 over negative p plus 1. Now, for the first case, we know that natural log goes to infinity, so this is just infinity if p is 1. For the second case, what happens when t goes to infinity? Well, it depends on the exponent. If the exponent is negative, if the exponent of infinity, this is infinity, if the exponent is negative, then that would approach 0. So this would approach 0 minus 1 over minus p plus 1 if the exponent negative p plus 1 is negative. So that would be a finite number. Otherwise, if the exponent negative p plus 1 is positive, if the exponent is positive, we get infinity to a positive number, and that would be infinity divided by a positive number, so that's also going to be infinity. So as we see, this is the only case that this converges. So that means when p is more than 1, it converges. And when p is less than or equal to 1, it diverges, which is what the p-test tells us. So let's look at the next test. The next test is what we call the comparison test. Suppose you have two sequences an and bn, and they are both positive, and one of them is less than or equal to the other one. If the smaller series diverges, then the larger one also diverges. If the larger one converges, then the smaller one also converges. So this is the comparison test. It's very similar to the comparison property that we have seen for integrals. Let's look at a few examples on this one. So the first one is the sum of 1 over n squared plus 5, n equals 0 to infinity. This is an instance that you can apply the integral test as well, because you can integrate 1 over x squared plus 5. This is one of those tangent inverse problems. But you can also use comparison tests. So if you look at 1 over n squared plus 5, this is less than or equal to 1 over n squared. Well, the only issue is if 0 is at the bottom, that is not going to make sense. So we're going to assume that n is at least 1. Because again, we can separate this sum from 1 to infinity and then from 0 to 0. It's basically the first term would be 1 over 5. The rest of it, we have to see if it converges or not. So now, what we know is the sum of 1 over n squared, n equals 1 to infinity. This converges because it is a 2 series. So p equals 2 and 2 is more than 1. So this converges. Now by comparison test, the sum of 1 over n squared plus 5, n equals 1 to infinity, also converges. So this is a finite number. Now if you add the very first term, which is 1 over 5, that would also converge. So this means the sum of 1 over n squared plus 5, n equals 0 to infinity, also converges. Let's look at the next example. Next one is 2 plus sine n over n. So this is definitely something we cannot integrate. So let's try the comparison test. So if you look at 2 plus sine of n over n, well, this is less than 3 over n because sine is at most 1, so 2 plus 1 is 3, and greater than or equal to 1 over n. And of course, everything here is positive. Why? Because sine of n is greater than or equal to negative 1. Now, if you look at the sum of 1 over n equals 1 to infinity, this diverges because it is a 1 series. So it's a p series with p equals 1. So this diverges. So now that this diverges, the larger one also would diverge. So by the comparison test, the sum of 2 plus sine of n over n also diverges. Okay, so let's look at the last example on this one. So the next one is 1 over 4 to the power of n plus 7. So we can compare this one to a geometric sum. So we have 1 over 4 to the n plus 7. This is less than 1 over 4 to the n. And everything here is positive. But this one is a geometric sum. It's 1/4 to the power of n. And we know that geometric sums converge if the common ratio is between -1 and 1. So we know that the sum of 1 over 4 to the n equals 1 to infinity, or I believe they started from 0, although again it doesn't really matter. This converges because it is a geometric series with common ratio 1 over 4, and 1 over 4 is between -1 and 1. So now, because the larger one converges, the smaller one also converges. Again, you have to make sure that both series are positive. So by the comparison test, the sum of 1 over 4 to the n plus 7 also converges. Okay, so the last thing we're going to talk about is what we call the limit comparison test. Sometimes directly comparing two sequences isn't very easy or even possible. You have to write down inequalities, and inequalities aren't always easy to work with. But what you know is that the ratio of these two sequences is approximately a fixed number. So in other words, at infinity, the ratio is basically the same. So that tells us that an is approximately L times Bn, which tells us the sum of an is approximately L times the sum of Bn. And if L is not 0, the sum of Bn would be approximately 1 over L, the sum of an. So if this one converges, then this would also converge. And if this one converges, then this would converge as well. So if one converges, the other one converges, which means either both converge or both diverge. However, for that to happen, we need this L to not be infinity and also not be 0. So it has to be a finite positive number. So let's look at an example on this one, and then we will summarize. Determine if this converges. So we'll take one of the sequences to be n squared plus 3n over n cubed plus 5. And the other one, we're going to look at an approximation of this one. What's the dominant term on top? Well, that is n squared. What is the dominant term at the bottom? That's n cubed. So when n is very large, these two sequences are almost the exact same thing. So we're going to take the ratio of these two, an over bn. So that is n squared plus 3n over n cubed plus n, multiplied by reciprocal of bn, which is n cubed over n squared. Now, we want to find the limit of this one. There are a couple different ways of doing that. One way would be to simplify this. We get 1n, and then multiply, we get n cubed plus 3n squared over n cubed plus, this is 5 plus 5. So that's one way. Now if you take the limit of this one, so let's take the limit of an over bn as n approaches infinity. That's the same as the limit as n approaches infinity. So the dominant term on top is n cubed. Dominant term at the bottom is also n cubed. So that is 1. Now since 1 is a positive number and it's also finite, either both series converge or both series diverge by the limit comparison test. So as you see, I specified the test that I'm using and I also checked the conditions. Now we'll have to check if one of them converges. Let's look at the sum of Bn. Sum of Bn is the sum of 1 over n equals 1 to infinity, because what we are given is n squared over n cubed, which is 1 over n. That's what we came up with. And we know that this series diverges because of the p-test. So by the p-test, this one series diverges. Okay, so if that diverges by limit comparison test, the sum of n equals 1 to infinity also diverges. So that's the answer to the problem. Finally, we're going to summarize what we did in this video. We talked about essentially 3 different tests. The first one was the integral test that tells us if you have a function that is continuous, positive, and decreasing, then if the integral converges, then the series converges. If the integral diverges, then the series diverges as well. We use the integral test for sequences that are decreasing and positive, and evaluating the integral is easy. We use comparison test if we have one series that we can compare with another one that is simpler. And I forgot to include the p-test. So the p-test tells us that the sum of 1 over n to the power of p converges if p is greater than 1. Otherwise, it diverges. And finally, we have the limit comparison test that tells us if you have two sequences that are again positive, everything we did in this video is about sequences that are positive. If the ratio approaches a finite positive number, then these two series behave the same, which means if one converges, the other one converges. If one diverges, then the other one diverges. And that brings me to the end of this video. I will see you in the next video.